The Laplace transform is a mainstay tool for engineers, and the reason for that is because it takes complicated university level math, calculus, differential equations, and turns it into high school algebra. The only caveat is that it's algebra with complex numbers. And so more technically, it's an operator that maps functions to functions, but maps real functions of time into complex functions of s, which we'll often denote or call frequency. So the definition of the Laplace transform, if you remember anything about the Fourier transform, it's a very similar idea. In this case, we denote a small f of t as a function of time, and the Laplace transform is a capital F, typically, so the capital letter, of a complex number s, and we define that to be the integral from 0 to infinity of that function of time times e to the minus st. And that's an integration with respect to dt. So that means that we integrate away t and we're left with a function of s. So again, we start with a function of time, scalar function of time, and we map into a complex function. So it gives us challenges in visualizing it, like we discussed in one of our prior videos. There is a reverse or inverse Laplace transform defined like this, and it allows us to go from a f of s, capital F of s, back to the small f of t, the function of time. So typically, we will not use the explicit definition of the inverse, and only at the beginning will we start to use the definition of the forward Laplace transform. And that's really just like when you learn the derivative the first time, you learn some technical details about it, but then it becomes an operational tool to allow us to transition between time domain functions to s domain functions. And so we won't come back to this original definition after we've essentially composed a table of types of functions that we typically see. And so a lot of what we'll be doing in this next class will be about building out the tables and understanding the properties of the Laplace transform. So let's go ahead and apply this to a step function. So if we have the step function, which is essentially 0 before t is equal to 0, and it's 1 after time is 0, so it's 1 when time is positive, and we integrate this, so the integration goes from 0 in time to infinity time, and we're just multiplying then by 1 times e to the minus st. And so you just treat s as a parameter, and so that means that the integration is just minus 1 over s times e to the minus st, and we evaluate that at 0 and infinity. So at 0, e to the minus s infinity is 0, and then the second term, when t is 0, we just get minus minus 1 over s. And so the solution there is just 1 over s. So the Laplace transform of the step function 1 is equal to 1 over s. And so if you see 1 over s and you want to take the inverse Laplace transform, the inverse Laplace transform of 1 over s is in fact the step function. So the exponential function goes as e to the minus at, where a is some parameter that we would choose. So that could be 2, that could be 5, could be anything. And so if we can calculate the Laplace transform of this, we insert e to the minus at, and so there's some nice combination that we can do with that exponential. So that exponential becomes e to the minus quantity s plus a times t. And so that allows us, if we treat s and a both as parameters, we can just find the integral of that. So we get that minus 1 over s plus a out front, and then we evaluate it again from 0 to infinity. And so that gives us 1 over s plus a. So the Laplace transform of e to the minus at is 1 over s plus a. And so an interesting thing to note, and an important technical detail, is the fact that the Laplace transform, you need to be careful that the integral actually converges. And so if we had a value, we need to be careful of where we allow our Laplace transform capital F of s to exist, because in some cases the integral here may not converge. And so, for example, let's take a look again at that exponential. So we just combine that, and maybe I just write it as a plus s instead of s plus a, it's suggestive in that exponential in the solution here that if the real part of s is greater than minus a, then that means that we will converge, because that means that overall exponent parameter minus a plus s is going to be less than 0. But if minus a plus s is actually greater than 0, then that means as t goes off to infinity, that means that exponent is also going to go off to infinity. So that exponent parameter needs to be negative, otherwise it won't converge. So along with this solution, technically we need to add this addendum that says the real part of s needs to be greater than minus a, otherwise the Laplace transform explodes, it doesn't converge, and so we can't really define the Laplace transform. So this won't be a detail that we need to consider too deeply, but it's good to be aware of this when you use this technique. And the last one we'll do in this video is the impulse or delta function. And so if you remember the delta function, it's essentially this pulse that happens in instantaneous time, and it's infinitely large, but has kind of area. We see it as having area of 1. And so the best way to think about that is take this temporary step function that essentially has value 1 over t for t amount of time. And so that means that area there is 1. And so if we take that capital T, if we take that getting smaller and smaller and smaller, but maintain the area is equal to 1, the height of that gets taller and taller and taller. And as we get infinitely narrow, the pulse gets infinitely tall. And so the function, one of the consequences of this is the fact that when I take the integral of a function, as I'm looking in green now, the consequence is that the integral of a function h of t, when I multiply that by delta t, is that it just picks out the height of that function at the value of delta. So delta here is located at 0, and so it picks out the height of h at 0. If we had delta of t minus a, then the delta would be located at a, and so you'd evaluate h at a, at t is equal to a instead. And so if we calculate the Laplace transform of this, we get delta times e to the minus st, and that's equal to simply just 1. And so the Laplace transform of the delta function is 1.